Hello again, my faithful physics fanatics. How are you today? Hope things are going well. Today we get to do a pretty fun little lecture. We're going to do circles, but we're going to do circles vertically. So this is number 3 in the forces and circles lectures, but today we're going to talk about circles that are up and down. So just looking at these, upper left we see lots of circles and loops and stuff. Upper right, we see something going over the top of a hill, like a roller coaster or something. And we actually in physics model a lot of those hill tops as circles. And then you can see the roller coaster is going to go down to the bottom of a hill next, and we can look at that as a circle too. Um, Bottom left picture, there we are again with some circles, and hopefully you can see the top of the hills look like circles. Bottom right, there's a car that has gone over the top of a circle fast enough. The velocity going around the circle has been fast enough that actually the car went off the ground. We'll talk about that as well. Um, so, vertical circles. Look at the diagram there. We still have our velocity and our mass and our centripetal force. But in this case, what we're going to have is the force of gravity is going to be in this picture now as well. I'll go ahead and I'll put that in black as well. And so we have the force due to gravity, which will be pointing, in this case, to the center of the circle, pointing straight down. Again, pictures of some situations where we'll see this. So this one gets kind of fun. We get to have things fly off of circles. We get to do loop-de-loops, all kind of fun stuff. So, all right, here we go. Um, Let me give you a hint, and I can't remember if I mentioned this, but I don't think I did, that when you're doing a circle problem, if you want, what you can do is all the time, whenever you're using an FBD, you can make positive towards the center of the circle. Okay, so if I'm looking at the situation where the mass, whatever it is, a car or you know, a ball going in a circle or whatever, is at the top of a circle, I would put positive down in this case. Now you don't have to do this, but what it does do is it gives you a kind of a standard way of approaching each problem, and that's what I'm going to show you here when we do our problems today. All right, so positive will always be towards the center of the circle. All right, let's talk about a car going in a valley. So in this case, you know, this part of the circle isn't actually there. I just put it there so you could imagine. But we've got a road going downhill, and we go into the bottom of a valley, and we go back up. All right, here we got a radius. We have our velocity of our car, and then when it's in the circle, the acceleration is straight up, or straight, I should say, towards the circle, towards the center of the circle. Let's go over to the right-hand side here and do a free body diagram for this situation. I'm trying to get a standard way to do this. I'm gonna put things that are not forces in red, and then we'll do forces in a different color. We'll try blue, see if that works out. All right, so do an FBD for me for this this situation. Okay, go ahead and do that, and then set me going again. So we're going to have the force of gravity down, and we'll have the normal force pointing up. Okay. After an FBD, what do we always do? Well, we jump straight into Newton's second law. So as we do this, we're going to need one of these positive and negative, and in this case, we're going to make positive up because he's at the bottom of the circle and we're going towards the center. So Newton's second law, and we're going to do it in the up and down direction. All right, we have some of the forces equals ma. Some of the forces we have normal minus force of gravity equals m, and I'm going to jump right into circular motion. While we're in a circle, acceleration is v squared over r. Okay? I want to give you a little hint here that might help a little bit when you're doing Newton's second law. Left side of the equation, forces on the system. Okay? Right side of the equation, motion of the system. Okay, the right side is always how it's moving. Well, at that instant, it's in a circle, so we put A as v squared over r. And at that instant, the left side is the forces that are acting on the system. Okay, system being the car in this case. All right, so from here, what you could do is, let's say, how big is the normal force? Well, just move force of gravity over. Normal force equals mv squared over r plus the force of gravity. So the normal force is more than the regular force of gravity based on the fact that the thing's going in a circle, the car is going in a circle. Okay? If v was 0, if he was just sitting there, the normal force would be gravity. But because the road has to push the car in to go into a circle, the normal force is greater. I could ask you at this point if I knew the normal force and the mass of the car to find the velocity, to find the period if it went into a full circle, those kinds of things. I'm not going to do that. I just wanted to show you how to set this thing up. Let's do another problem. Now, the car is at the top of a hill. Again, this is just here to visualize the circle. We have our velocity. What I want you to do is FBD this car right here. Go ahead and do that, and I want you to pick positive and do Newton's second law for me. Do all those. Pause me while you're doing them, and then start it up again and see if we did it right. All right, here we go. I am going, in this case, to choose positive as down because that's towards the center of the circle. Again, you don't have to do that. I just like to do that. Let's FBD right over here. We have the force due to gravity. All right, and at the top, we have the normal force. Exactly the same. Now notice, I don't on the left side put down the force, the centripetal force, or the anything else. I do whatever the forces are on the thing, on the object, on the system. On the right side, the F equals ma, the A I put in v squared over r for the circular motion. All right. Newton's second law in the up and down direction. We have sum of the forces equals m times a. And this time, positive is down. So we have the force of gravity minus the normal force equals m v squared over r. Let's find the normal force in this case. Minus the normal force equals m v squared over r minus the force of gravity. Now I don't want minus the normal force, so I'm going to multiply everything by -1. So that'll change the sign of each term. Minus mv squared over r plus the force of gravity. I'm going to switch those two terms on the right side just to make it neater. Force of gravity minus mv squared over r. Check it out, you guys. This time, the normal force has been decreased. It's the force of gravity minus how fast the guy is going over the loop. If velocity was 0 here, the normal force would be just the regular force of gravity. Let's jump back to the last slide. What did we end up with? What was our answer? The normal force equals the force of gravity plus mv squared over r. At the bottom of a circle, all right, you're going to feel heavier in a car. At the top of a circle, going back to our problem now, you're going to feel a little less. Hey, guess what? I could make the normal force 0. If I make v squared big enough, pretty soon the force of gravity minus mv squared over r could be 0. If I make v bigger and bigger and bigger, pretty soon normal force is 0. What happens if the normal force is 0? If the normal force is 0, I'm not on the road anymore. I'm in the air. That's how I go over a jump at the top of a hill. I go fast enough and the normal force drops to 0. Okay? So there's roads. All right, roller coaster loops. Same idea. All right? I want you to draw for me all 4 free body diagrams. That's all we're going to do on this one. Okay? I'm going to do the free body diagrams just outside the circle. Okay? Now, this time, let's say it's a roller coaster or it's a car just going really fast on a loop. So this is a looped track. Okay, so go ahead and do those, and then I'll see if you match what I did. I'm going to write force of gravity on all these first. There we go. Now, let's put the normal force on. Which way is the normal force pushing the little car? Start at the bottom. Let's do that one. Normal force is up. Here, the normal force is to the left. Oh, check this one out. The normal force is straight down. And here, the normal force is to the right. Okay? So in this case, how we go about these is we just do F equals ma. And if we choose positive towards the center, we do exactly the same problems, okay? So I'm going to leave this one to you to work on for your video lecture problem, all right? This is this one and the next thing I'm talking about are kind of exactly the same thing, all right? Let me show you what's next. Next, we have strings in vertical circles. There's no normal force, okay? There is a force of tension in the string. So let's draw a free body diagram of this mass, I don't even know what it is, being swung in a vertical circle. We have force of gravity down, and which way is the string pulling on this? String is going to pull straight down. So it's exactly the same as the last picture, but instead of the normal force, we use the force of tension. All right? That's the only difference. So what's going to happen down here? We have the force of gravity down, and we have the force of tension going up. So now that string has to do the v squared over r pull as well as the force of gravity pull, and that's where strings break usually, is in the bottom of a loop. Okay? So the kind of problems you're going to see is how fast can I swing it if the string can hold, for example, 10 newtons of force. Okay? This problem, the last one with roller coasters, what they'll ask is up here at the top, how fast can I go and make the normal force drop to 0, be weightless or feel weightless at the top, excuse me. Okay, so we're going to do a lot of problems with this. This is just kind of an introduction. I want you to see, here's our string problem again. I want you to see if you can do this spinning problem. This is kind of cool. We're swinging a bucket with water in it. So I want you to think about the water as your system and the bucket as pushing a normal force onto the water. This is a great problem to work through. Okay? Now, very important. I want you to leave everything in numbers. We're going to be doing more of these with numbers. It's a great problem to do, and I want you to check and see if you got it right. Okay? I mean, come in and visit to see if you got it. Alrighty, well, that's vertical circles. Enjoy yourselves. Have an awesome day.